Okay, let's do problem number 11 on page 283, and here it is in the book. Zoom in here. Let's read it carefully. It says, in a slow pitch softball game, a .2 kilogram softball crosses the plate at 15 meters per second at an angle of 45 degrees below the horizontal. The batter hits the ball towards center field, giving it a velocity of 40 meters per second at 30 degrees above the horizontal. Determine the impulse delivered to the ball. If the force on the ball increases linearly for 4 milliseconds, hold constant for 20 milliseconds, and then decreases to 0 linearly in another 4 milliseconds, what is the maximum force on the ball? Okay, so I assume that's kind of the part of this that's the most difficult. So let's write out what's given. So we've got the ball. Here's home plate, but it's crossing home plate. So here's the ball, and the mass is equal to 0.200 kilograms, right? And it's going 15 meters per second at an angle of 45 degrees below. So it's, whoops, that's not very good. Let me draw a little bit better now. So, it's 45 degrees, like something like that. So this is what the ball's doing before it's hit. And what's the velocity here is 15 meters per second, right? And it gets hit. So this is kind of the before it gets hit. Now after, the ball is, here's the ball, and it's moving at 40 meters per second at 30 degrees above the horizontal towards center field. So it's going the opposite direction. 40 meters per second at 30 degrees above the horizontal. Yeah, that's not very good. But this is, so this is V initial, this is V final. And it's going 40 meters per second, and it's going at this 30-degree angle. And then find, well, for A, we want to know what is the impulse on the ball, right? Off camera, dang it, okay. So, determine the impulse delivered to the ball. I'm going to use I like that for impulse. And then B, we want to know what is the maximum force. And here's what we've got time-wise. Here's how to set this up. We've got force here, and we've got time here, and these are in milliseconds. And it ramps from 0 force. It says if the force on the ball increases linearly for 4 milliseconds, so 1, 2, 3, 4, and this will be time in milliseconds. So it's going to ramp up to some maximum value. Then it's going to stay constant for 20 milliseconds. Oh, I should have changed the scale. I'm just going to put a zigzag here. This is 4 milliseconds. 20 milliseconds, and then it's going to ramp back down in another 4 milliseconds. Okay, and so now the impulse on the ball, the maximum force, well, it's going to be, the impulse on the ball is represented by the area of that. So if the area of this, we'll set it equal to that, and we'll solve for that force. So let's solve this problem. Well, we know that the impulse on the ball is equal to the change in momentum of the ball, right? I mean, that's the impulse momentum theorem. And so first thing we need to do is figure out what is the change in momentum of the ball. And so, well, this is going to be the final momentum minus the initial momentum. And so, well, what's the final momentum? Well, it's right here. Now, this is this is a vector in polar coordinates. Of course, we say this is 30 degrees here. That was given in the problem, but if we just have our xy coordinate system look like this, you know, x and y, then we can say that this angle is 150 degrees. So, so we're going to have v final. Let's get v final in rectangular coordinates. So it's going to be 40 meters per second times the cosine of 150 degrees, and then we'll put 40 meters per second times the sine of 150 degrees. And so we need a calculator. So this turns out to be negative 34.6. 4, we'll carry 4 significant figures just for now, meters per second. And then oh, well, of course, this will be 20. Didn't need a calculator for that. So that's the final velocity. And so we can get P final. It's just the mass times that. So we'll multiply these by 0.2. So 34.64 times 0.2 is, this is negative 6.93 kilogram meters per second. In the x direction, and in the y direction, well, 0.2 times 20 is 4, right? So that's going to be 4.00 kilogram meters per second. It's all right, it happens all the time. All right. So that's our final momentum in rectangular coordinates. Now we just need to do the same thing for the initial. P initial. Maybe I can speed things up here a little bit. Let's just multiply by the mass, 0.2 kilograms times, well, it's negative 45 degrees, so this is going to be 15 meters per second times the cosine of negative 45 degrees. And that's the x component of the momentum, and then 0.2 kilograms times 15 meters per second times the sine of negative 45 degrees. And so, has anybody done this problem? I can type it in my calculator, but what do you get for the x component? Anybody done that yet? What is it?
Oh, I'm sorry, I didn't do that.
Okay, so 0.2, let's clear it, 0.2 times 15 times the cosine of negative 45 degrees. And you get 2.12. And the units there are kilogram meters per second. That's the x component, the y component. I get, oh, well, duh, negative 2.12. I didn't need to do that twice. So all I have to do now is subtract these two guys. This one minus this one minus this one. So the change in momentum will be equal to negative 6.93 minus 2.12. It's negative 9.05 kilogram meters per second. And for the, let's see, that's going to be 4 minus negative 2.12. And we get positive 6.12 kilogram meters per second. Now let's see if that makes sense. The ball's coming down like this. I need to change its momentum quite a bit in the x direction, but it's going to go this way. So a big negative change, and instead of going down, it's going to be going up. So I have a big upward change in momentum. So this makes sense to me. And that's always a good thing to do when you're doing a problem, is stop, check, say, does this make sense? Based on what we're trying to do. And it does, at least does to me. Now, I think that if we're going to get this force, now this is an answer. I don't think it says, I mean, this is the impulse on the ball. It's a change in momentum of the ball. It is the impulse, but we're going to want the maximum force, like the magnitude of the maximum force. So what we're going to do is express this in polar coordinates. And actually, all I really need is the magnitude right now. So remember, this is equal to the impulse. Does anybody check this in the back of the book? Was it in this form, or is it in?
9.05. It says positive 9.05 and positive 6.12.
Well, there's no way that's true. There's no way it's not a negative change in momentum. I mean, look at the picture. I mean, assuming when you hit the ball, it's moving in the opposite direction than when you threw the ball. I mean, I'm assuming it's coming down like this towards home plate. It says it's hitting it towards center field. So, oh, you know what? They may have had home plate on the left side, and center field is to the right. So that's not a big deal. That's just the axis system I chose compared to what they chose. So not a big deal. So now that we know what the change in momentum is, we also can figure out, well, this is, let's figure out what the magnitude is. The magnitude of the impulse is equal to the square root of 9.05 squared plus 6.12 squared in kilogram meters per second. And of course, if it's an impulse now, a kilogram meter per second is really a Newton times a second. So we can kind of make that change. So the impulse is, let's see, 9.05. Oh, where's the square button on this calculator? Squared plus and then we need to take the let's see, is that 10.9? Is that right? Okay. So this is 10.9 Newton seconds. Okay, so that's the answer for A. Actually, this is the answer for part A, but here's the maximum impulse. Now what we need to say is this, that this value is the area of this trapezoid up here. So let's say, here's my maximum force. And so the and the area of a trapezoid is the average base times the height. So, and it's the height we're looking for. So 10, so the area of this whole thing is 10.9 Newton seconds. That's the area of this thing right here. So 10.9 Newton seconds will have to be equal to the area of this, which is the base. Now this base here is 28 and this is 20. So it's 28 milliseconds plus 20 milliseconds divided by 2 times my maximum force, which is really the height, right, of this trapezoid. So 28, that's 40, that's going to be 24 milliseconds. So we'll divide by 24 milliseconds. So 10.9 Newton seconds divided by 24. Well, milliseconds, right, is a thousandth of a second. So we'll go 0.24 seconds. And that should be my maximum force. So F max equals 10.9 divided by 0.024 equals 454 newtons. Is that right? What answer did they get? Oh no, they did?
Yeah, but I'll check it.
Well, okay, that would be easy to do because this is the impulse. So all we have to do is do what I did up here, but and so anyway, this is the magnitude of the maximum force, and we can figure out the angle by using inverse tangent. But it turns out to be right. Okay. But in rectangular form, you would just say, well, look, we're dividing by this 20, this 0.024 seconds. If I divide these components by 0.024 seconds, I should get the components of the force. Did that work? Does that work? Let's try it. So I'm saying that the maximum force will have, well, negative 9.05 divided by 0.024. So negative 377, is that right? I think they might have made it positive. So negative 377 newtons, that's the x component, divided by, and this is 255. You can put it in IJ. Sometimes I'll do it like X and Y. And some of you fancy people in Math 6, you put like little sharp corner things on here. Is that right? And so, but anyway, this is the maximum force in rectangular coordinates. And mine is negative because because of the way I drew the direction of my coordinate system and the way the ball came in and the way the ball left. I guess the book did it the other way. They showed but it doesn't matter. Okay? Let's zoom out so everyone can see the whole thing. So there you go. That is a pretty tough problem. Yes? The what? Oh, where did I get the 10.9? This right here? Okay, well, what I said was that, and this is kind of the big idea of this problem, the change in momentum of the ball is equal to the impulse of the ball. And the impulse can also be represented as the area of a force versus time graph. So the force started at 0. The book said the force started at 0, and then in 4 milliseconds moved up to its maximum force, then stayed constant for 20 additional milliseconds and down here. So this right here is a trapezoid. And the area of a trapezoid is the average base times the height. So this has a base here of 28 milliseconds. This base right here is 20 milliseconds. And the height is my maximum force that I'm looking for. Okay. Any other questions? Okay.
Oh, the whole area was 10.9.
Yes. Well.
Oh, shoot, I was looking. I was like.
No. The area has to be 10.9 Newton seconds because that was the impulse placed on the ball, and we got that impulse on the ball from the change in momentum of the ball.
Yeah.
So this has to be 10.9 based on my answer in part A.
Yeah, I got confused for a second because I thought, like, for some reason, I thought you meant that the 10.9 was just like the box part of the triangle, the trapezoid, and I was like, what?
Okay.
I got it. Don't worry.
Very good. That's all.